right. Okay, so last time we learned this theorem. Let's recall. And we were in the middle of the proof of this. So the theorem of highest weight. And there are 5 statements. So every irreducible representation. So everything is about SL3. So every irreducible representation is a direct sum of weight spaces. So it's like a weight spaces. And second, every irreducible representation has a unique highest weight mu. 2 irreducible representations with the same highest weight are isomorphic. 4. The highest weight mu is of this form, pair of non-negative integers. And 5, for every such pair, there exists highest weight, or just irreducible. Irreducible is basically highest weight. Irreducible representation with highest weight, this. So this is the theorem that we want to prove. And in fact, last time we proved the first 3 things. We proved that every irreducible representation is a direct sum of the weight space. Every irreducible representation has a unique highest weight, and for any two irreducible representations with the same highest weight, they are isomorphic. And then now today we're gonna prove the remaining 2 statements. Okay. So everything after the theorem, every irreducible representation is just a highest weight representation. The highest weight cyclic representation with a unique highest weight. All right, so proposition 6.15. Suppose that we have 2 irreducible representations. Maybe U. I think it should be W. Yeah, 2 irreducible representations with highest weight mu, the same highest weight. Then they are isomorphic. So it's a uniqueness of highest weight representation with a given highest weight. So proof. Let's consider highest weight vector. So these are highest weight vectors for each representation. And consider this space, the direct sum of the 2 representations. And this argument is similar to one of the homework problems you did before. So let U be the subspace of V direct sum W be the smallest subspace containing V. So this is a space here, V plus, or V plus W, but we will write this way. Then, by definition, because it's the smallest containing this, and this is also a weight vector with the same weight, mu, because it's just a sum, direct sum. then U is a highest weight cyclic. And we assume the fact that every finite dimensional representation is completely reducible. So this is completely reducible, and by one of the propositions we proved last week, U is irreducible. We showed that every highest weight cyclic is irreducible. Okay? Now, so we have irreducible space, subspace inside here, and the projection maps, consider the projection maps P1 to V and P2 W. And these are intertwining map. Yes, these are, they respect the action. And if you restrict, so because U is inside here and also here, if you restrict your projection map to U, to U to W, these are also intertwining map, and also non-zero intertwining. Why non-zero? Because it's a projection map, so both contains this vector, right? V, W. This gets mapped to where? Just V. And the same thing here gets mapped to W. It's a non-zero, right? Highest weight, these are highest weight vectors, so non-zero. So it contains a non-zero stuff here. So, but these are all irreducible. This we show that's irreducible. Intertwining maps between irreducibles are either zero or isomorphism, but they are not non-zero. So by Schur's lemma, isomorphism, we get V and also W. So that's it. We proved it. And more accurately, maybe I should have said, like, because of the first one, U is isomorphic to V. Second one, U is isomorphic to W. So that's why V is isomorphic to W. Okay. So any two irreducible representations with the same highest weight are isomorphic. So this is the fourth statement of the highest weight, the theorem of the highest weight. Now we are left with the last statement. But before that, oh yeah, actually I think we have to show one more thing. I think that was the third one, and the fourth one is this. Every highest weight is a pair of non-zero integers. Irreducible representation of FCL3 with highest weight mu, say M1, M2. Then these are integers, non-negative integers. Proof. Actually, the proof is really simple. Let V be a highest weight vector with this highest weight mu. Then pi of x1 V equals, this is the definition of the highest weight vector. This is 0, right? If you apply x, it's going to be 0. And we restrict the restriction of pi to SL2C. If whenever we have a representation of SL3, we get an induced representation of SL2 by restricting the action to this. But this is what? Basically, this is the span of H1, X1, Y1. This is a representation of SL2. With what? With this property. If we have apply H1, it's going to be M1V, because this the weight is this. And if you apply x, it will be 0 because of this, highest weight. But we showed this in chapter 4, proposition 4.34, M1. In this case, we showed that every eigenvalue is an integer. So in this case, in addition, if we have this, that is the highest or largest eigenvalue, and is always a non-negative integer. We showed this. And similarly, we can do the same thing. We can show this using every index 1 replaced by 2. We get this. So that's the proof. It's quite simple. We just use the result from SL2. So this is the fourth proof of the fourth statement. Now, finally, we are ready to prove the fifth statement. The statement is the converse of this. For any such pair of non-negative integers, we have a irreducible representation with that specified highest weight. That's what we want to show now. Okay, let's do that in the next page. Because it's going to be a little long. F1, M1, M2 non-negative integers. Then there exists irreducible representation of SL3, of course, with highest weight mu. And of course, this must be unique because we already showed that it's unique. Uniqueness is already done. So proof. We will just construct such an irreducible representation. So it's a constructive proof. So, by the way, if M1, M2 equals 0, both 0, then the trivial representation V, which is of dimension 1, so action is just everything sends a vector or complex number to 0, the trivial representation. This is such an irreducible representation, right? So it's done. For 0, 0, everything just, if you apply anything to any vector, it's just 0. So eigenvalue is of course 0 for H1, H2. So, and it's of course irreducible, so done. So we will assume that it's non-zero vector. Suppose that one of these is non-zero. Okay? And it consists of several steps. So first step is we will first construct what we call fundamental representations having weight 1, 0, 0, 1. Construct two representations with highest weight 1, 0, 0, 1. These are called fundamental representation. And these weights are called fundamental weights. And in fact, there is a nice one, standard representation. What is the standard representation? So representation of SL3 is an action on a vector space. So SN3 action on a vector space. And there's a very natural action because SL3, elements in SL3 are just 3 by 3 matrices. So it acts on C3 very naturally, just by matrix multiplication. So that's called the standard representation. The standard representation is just is the representation V, which is a vector space C3 with the natural action or standard action. So x V is just x times V. As a matrix, just three-dimensional vector, we can multiply them. Just a matrix multiplication. Via this. Okay. And so if you want to write this as, for instance, or in other words, i.e. pi x is just x. Pi of x is just x. Pi x, if you apply V, this is x times V as the multiplication. Okay. Then in fact, this is irreducible. So easy. Check. You can check it. It's irreducible. So we will assume that is effect. And then we can find the weight vectors. So E1, E2, the standard basis. These are weights. Weight vectors with weight. So the first one is 1, 0, minus 1, 1, 0, 1. Also easy to check. All you need to do is multiply H1 to this. And what is H1 times E1? Just E1. So it's 0. Oh, sorry, 1. So what is H2 multiplied to E1? 0. Is it 0? Yeah, it's 0. So 0. It's like that. So apply H1 to this, it will be minus 1, minus E2, etc., etc. So I'm not going to do the details, but you know how to do that. So these are weight vectors with corresponding weights like that. So for instance, this is the highest weight. This is the highest among this. So we have this partial order on the weights, among the weights. This, if we say this is, okay, let's not say anything about that. This is 1, 0 minus alpha 1. What is alpha 1? 2, minus 1. If you subtract alpha 1 from here, you get this. And what is this? It's 1, 0 minus alpha 1 minus alpha 2. So what is alpha 2? Yeah, we will use this like a lot of times, so let's try to remember this. So anyway, this is the highest weight, and these are like linear combinations. They are obtained from this by subtracting these positive simple roots. So this is highest weight representation with highest weight 1, 0. We just constructed such a thing. Okay? This is done. So this means a standard representation. What about this? It's going to be the dual of the standard representation. So the dual of the standard representation is given by, so dual, when you have the usual, when you have a representation, what is a dual? The dual is defined to be minus transpose, minus and transpose. So if pi prime is a dual, or how did we write dual? This way. This is defined to be minus pi z transpose. Yeah. But in this case, pi is just an identity map, so it's minus z transpose. Let's write this in just for this way. There's notation. Because we will be using this many times, it's a little bit complicated to write this all the time. Then irreducible is also irreducible, and E1, E2, E3, these are also weight vectors with weight, corresponding weight, minus 1, comma 0, minus 1, comma minus 1, 0, comma 1. So in this case, this is the highest weight. Okay? So this is the highest weight vector. So we constructed this. Standard representation, dual of that. So step 1 is completed. Is this okay? So now we have these basic building blocks. Highest weight representation with this, and also highest weight representation with this. But we want to construct arbitrary pair M1, M2. But we can do that by combining these two representations. Okay, that's the step 2. So step 2. Let's say pi 1 v1, the standard representation, and pi 2 v2, the dual of the standard representation. Standard representation. Okay, so we know that this is highest weight representation with highest weight 1, comma 0, and this for 0, comma 1. And also, let's say v1, which is in fact, you can take e1, so with highest weight vector, and here v2 is going to be e3 is the highest weight vector for this representation. Okay. And now we will construct the representation. Define the representation which we denote pi sub m1, comma m2 on v. We just make the tensor of them. So v1, v2, v1, like m1 times v2, v2, m2 times. Actually, it's the definition. When we have two representations, we know how to take the tensor product. So that's the definition. Then we can take arbitrary number of tensor products of representations. We just obtain this. And we know how the action, how SL action goes for this representation. Do you remember? So recall, in case you don't remember, V tensor W is the representation given by the action. What is the action? Okay, let's write it this way. Okay, I think in general situation, pi sigma, if these are representations, then let's say pi sigma rho is a tensor product, is a representation given by rho of x is what? Pi of x tensor identity tensor pi sigma of x. So in other words, the action is like, if we have something like this, the action of this is like we apply first vector and then add the thing that we got by applying the action to the second vector, etc. So what if we have many terms? If we have a tensor of n representations, then the action will be sum of n factors or n terms, where each term we have ith term, we apply this to the ith vector, like that. Okay. All right, and we define, so we know this representation, and we define M1 vector M1 comma M2 to be V1 tensor dot 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 V1, V2 tensor V2, and of course there are M1 vectors and M2 vectors like that. So this is an element in our representation. So this will be the highest weight vector. Then is a highest weight vector with, what is the weight? Highest weight M1, M2 as we wished. Why? Can you see that? All right, let's see if this is really a weight vector with this weight. What happens if you apply H1 to Vm1, M2? What is that? Because we have many vectors, we have a sum of many terms. So first we apply H1 to V1, and then V1, da da da, okay, plus H1 dot V1, da da da, okay, all the way to the last V1, H1, V1, tensor, V2, tensor, da da da. We have to go more. Now it will be V1, H1 dot V2, da da da, and more, right? But what is this? What is this part? If we apply H1 to V1, it will be, what is the eigenvalue? M1. Oh, sorry, what is the eigenvalue? 1, because this is the standard representation. So here we get just, in this case, we get V1, Vm1, M2, because this is just 1, this is just 1. This is also 1, so it's also Vm1, M2, all the way to up to this point. All the same vector. But what about this part? What is this? This is going to be 0 because if you apply H1 to V2, it's 0 because this highest weight vector with highest weight 1, 0, that means if you apply H2, the eigenvalue is, or the constant is 0. So everything this is 0. So the final answer will be this times the number of terms here, which is M1. So M1. So it's the same way we can show that if you apply H2, we get eigenvalue H2, or M2. That means this is really a weight vector with this weight. But how can we show that this is highest weight? What's the definition of the highest weight? Highest weight means if you apply x's, x1, x2, x3, then it will be 0. But do you see that? If you apply x to this, do you see it's 0? Again, we will have a bunch of terms, but everything we have at least one xi applied to V1 or V2. But V1, V2, they are already highest weight in their representation, so as soon as you apply x to any of these, it will vanish. So it is really 0 for everything after xi applied. So it's highest weight. That's the proof. Okay? So xi, v, mi, m1, m1, m2 is always 0. So it's highest weight. This is what highest weight vector means. So second step, we constructed a representation which has highest weight like that. But it's not yet done because this is not irreducible yet. But we are almost done because we can just find the smallest invariant subspace containing that vector. So step 3 is the final step. So let W be the smallest invariant subspace containing that vector Vm1, M2 in V1 dot dot dot, the vector space that we constructed. But then it is W is highest weight cyclic because the smallest. It satisfies all the axioms for the definition. Highest weight cyclic representation with highest weight M1, M2. We just constructed such a irreducible representation, but it is irreducible. We know that, so that's the proof. So this is the proof of the theorem of highest weight. Okay, this construction is really, the proof of this is constructive, so it's quite nice. And we can actually construct specific irreducible representations in this way, and we can understand the representations using this idea. And that's the topic in this section. Example. Highest weight 1, 1. So 1, 0, 0, 1, they are fundamental ones. And this is something that we want to understand now. We have a kind of we have a quite a satisfactory understanding of this. So recall, if this is irreducible, then we know that it is going to be highest weight cyclic with highest weight mu and highest weight vector v. You can say that. And then we also know that this vector space v is spanned by vectors of this form, of the form that are obtained from this highest weight vector by applying y's, y1, y2, y3, like repeatedly. You can make many vectors in this way, and then just make a span of that, and that will be v of this form. So pi, y, j1, repeated application. After this repeated application of y's to v, we get many vectors, and then there will in fact, if you select some of them, there you can make a basis for this. Okay, but in our case, since we know that y3, this is y1, y2, bracket y1, y2. This is just a simple thing to check. So what is applying y3? This is, because it's a representation, this will be y1 pi y2, right? But this, again, in turn, pi y1 y2 plus pi y1 pi y2. So after all, this is just a combination of things that are obtained by applying y1 and y2. That means we only need to apply y1 and y2 because y3 can be obtained by doing things like that. So we will only focus on y1 and y2 and what happens to that, to this highest weight vector. So enough to consider y1 and y2. So here we may assume that these j's are y1, y2. All right. Again, then we will say pi v, the standard representation. I think we wrote pi 1, v1, let's be consistent. And that means, i.e., pi 1 z is just z, the same as a vector. This action v1, which is C3. And let's say this is the dual of the standard. So, i.e., pi 2z is z bar, we will denote as z bar, which means minus z transpose, acting on the same space, acting on v2 is really the same. And we know that pi 1 has highest weight 1, 0 with highest weight vector. What is the highest weight vector? Do you remember? It was E 1, 2, 3. 1 or 2 or 3. 1. 1/3 probability. So we want to understand what happens if we apply y1 and y2 to this vector. So what happens if you apply y1? What is y1 times? This application is just, this section is just a usual multiplication of matrices, matrix and a vector. So what is this? E1, E2, or E3, or some linear combination of them. It's E2. Okay. Yeah, I will just list them. This is not something that you cannot do. Just a basic linear algebra. We will consider all this. Okay, for this standard representation. Okay, I think it's a little useful to visualize this using diagrams. So let's say V1, E1 is the highest weight vector. We can apply Y1 or Y2. Let's say the left direction, if you go left direction below, then let's say it's the result after applying Y1. So if you apply Y1, then we get E2, right? If you apply Y2, what do we get? 0. And here we can apply, here we don't have to worry about anything now, it's just 0. So what happens if everything we have, for every non-zero vector, we have two directions, Y1, Y2. Here, if you apply Y1, it's going to be 0. Here, E3. Now we have to do one more, but it's going to be 0, 0. So think of this as, yeah, maybe it's helpful to visualize like that. We will do this anyway for the whole 1, 1 representation. Now, for E2, for pi 2, we do the same thing. And this pi 2, the dual, has highest weight 0, 1 with highest weight vector. What is highest weight vector? E3. Yeah, in this case E3. But for some reason which will be apparent later, we will just write this as F3, which is just E3. Just to rename the vector. And we will also give another name to F minus E2. Let's say it's like that. Then F1, F2, F3, they form a basis. It's not completely necessary, but it is better if we do in this way. It will be much nicer using this basis. And let's consider what happens if we multiply Y1. This means, basically, this means pi 2 of y1, f1, right? We apply y1 to f1, then I'm going to just write this down. If you apply y2 to f1, it's going to be f2. This is just a simple computation that everyone should be able to do. Again, we can visualize this using the diagram F1. We have two directions. In this direction, Y1, but Y1 action is like multiplying this matrix, Y2. So what is this? Y1 is a 0, and here, Y2 and then F2. Here, apply Y1, F3, this 0, and now 0, 0. So we have a diagram like that. Okay, now it's time to consider the pi 1, 1, which is pi 1 tensor pi 2 acting on V1, V2. All right? So this is not, let's see. It turns out that this is a highest weight cyclic with highest weight 1, 1 with highest weight vector E1 tensor F1. But simply, let's write this, just for simplicity, let's write this way without writing the tensor. If you want, you can keep writing tensor, but let's drop that for the moment. So again, the space will be spanned by the vectors obtained by applying y1 and y2 to this vector. So let's see what happens. But to do that, we need to understand this. So pi 1, what is the y action? Yi. How does this act? Okay. Yeah, I wrote this already, but what is y? This is y. Yeah, y, that's right. Pi 1 y, but that's just y. So y tensor identity. Identity times pi 2, which is y bar. So it acts like this. So in this space, the SL3 acts in this way. So let's see what happens to this. Do I have enough space? I guess so. Here, we have two directions. We always have two directions, y1, y2. So we apply y1 or y2. What happens? This is tensor. First, we apply y1 to the first vector, and then leave it there, plus leave it there, apply y1 to the second vector. Okay? Okay, let me do this in this way. Okay, let me rewrite this everything just so that everyone can see. Oh, I think I wrote. This is the correct one, right? I'm just copying this and this. 0, 0, 0. What is F1? This is kind of the opposite. 0. Now we want to know what happens to E1. Okay, I think maybe it's better to keep this because we are not very comfortable with tensors. Let's just keep them. It's not a big deal to write this tensor all the time. So, all right. So what happens if you apply y1 to this? we first apply to the first vector, then we get E2, so E2 tensor F1. What if we apply Y1 to this? 0, so we don't have to write anything there. This is okay. What about Y2? Y2, 0. If you apply Y2 to this, so is that 0? No, we have to consider the other thing together. So first, keep this there, apply Y2 there. That's going to be F2. So E1 tensor F2. We have to keep doing this. Apply Y1, then what happens? Apply Y1 to this, 0. So we have to apply Y1 to F1, 0. So it will be 0. No, that's right. What about Y2? We apply Y2 to E2, E3. So E3 tensor F1. Now we have to apply we have to leave it there. Apply Y2 to F2. What is that? F2. So that's going to be E2 tensor F2. Everyone okay? Now let's do one more or many more. Apply Y1 to this first. It's going to be 0 for this. What about this? Y1 apply this, 0. So this will just vanish. Now what about this? Apply Y1 to E1, 0. So forget about that. So apply Y1 to F2. That survives. So E1 tensor F3. Now Y2, apply Y2. What happens to if you apply Y2? This is Y2, 0. So we keep this, apply Y2. What is that? F2. Something's wrong? 어디? 제가 이거 들어보겠습니다. E2. Okay. Yes. Is that right? Thank you. So where are we now? You get the idea, right? Any question? I think I've done enough examples, so now you get the idea. Because, we have to, let me just complete it then, without any further explanation. You know how to finish this. Now I'm going to now we feel very comfortable with tensor, so I'm going to just skip the tensor. It doesn't matter if you have introduced another 0. So yeah, this is the complete stuff. Everything now 0, 0. After that, 0, 0. If you want. So this is the complete diagram for the weight. So these vectors will span our vector space V1 tensor V2. Okay, but we will do a little more on this diagram. What is the weight of this? What was the weight of this? 1, 1. So let's write down the weight. So 1, 1. What is the weight of this? Can you compute that? The weight of this will be the sum of the weight of this plus the weight of this. We already know the weight of E1. What is E1? What is the weight for pi 1 of E1? It was like, what was that? Weight for E1, E2? 크게 안 들립니다, 잘. What was the weight of this for the representation pi 1? Oh, maybe I didn't write that down. Maybe I did. Yeah, I think it's here, right? This is the weight for H2, corresponding to H. Yeah, maybe I didn't write that down for F2. But anyway, if you know the weight for this, which is what? What's the minus 1, 1? What was the weight for this? 0? Something, and eventually it will be minus 1, 2. So something must be 0, 1. Is that right? Oh yeah, that's right, because it's the highest weight. You can do that. You know the weight for this with this, you can write it down, and then you can just add them together. That's one way to write down this weight. But there is another way. I think this is better. We don't have to consider this. We can compute directly from here. How do you know that this is, how can you obtain this from this? We learned something that's very nice. Yes, alpha 1. So if you apply y1, so you have a weight vector v. So if you remember h1, oh. So let's say v is a weight vector with weight mu. Then if you apply y1 to v, this is a weight vector, 0 or weight vector, right? Weight vector with, what is the weight? Mu plus alpha 1. Oh, sorry, minus, mu minus. For x, if you apply x, we get plus, but for this, minus. And we know alpha 1 is what? 2, minus 1. What is alpha 2? Minus 1, 2. So if you go this direction, you just subtract this, right? So here you subtract, or let's say add. We add, in this direction, if we go, say, in this direction, we add minus 2, 1, right, to the weight. If we go in this direction, we add minus of this, so it's 1, 2. 1, minus 2. So in this direction, we add this to this weight, which is minus 1, 2. So what about this? We add this. That is 2, minus 1. And what about, you don't have to worry about this. What is the weight of this vector? Add this. What's that? 0, 0. What about this? You add this, so it's minus 2, 1. 1, minus 2, and you get the idea, right? So let me just write that down by looking at my note. Oh yeah, by the way, how many vectors do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So the dimension is 13? Can you say that? Of course not, because we have some overlaps. For instance, these are redundant. They don't have to appear. So we have only 1, 2, 3, 4, 5, 6, 7, 8 vectors that are linearly independent. These are just the same things that appear already. So the dimension here is 8. Okay? And we know that irreducible representation has the weight space decomposition. So everything, you can find a basis vector consisting of weight vectors. So everything must be weight vectors. So that's why we can write down the weights. So what is the weight here? So let me continue. And okay, we don't have to worry about this. They are nothing. So what are the weights? Weights of this. Just a 1, 1. Minus 1, 2. What is this? 2, minus 1. What is this? 0, 0. But let's say 0, 0 appears twice, because weight multiplicity really matters. And minus 2, 1. 1, minus 2, minus 1, minus 1. So these are the weights, and these are the multiplicities. Everything has multiplicity 1 except this, which has multiplicity 2. So from this, we can kind of understand the representation, highest weight with highest weight 1, 1 pretty well. You will do one of the examples. One of the homework problems will be to understand, to study the irreducible representation like this. You can practice with the example. Okay, let's move on to the next section then. The Weyl group. So another important concept. In fact, there are two approaches to define the Weyl group. This will be the first approach using Lie groups. So we know that I briefly mentioned at the beginning of this chapter that this is isomorphic to SU3 complexification, where SU3 is the Lie algebra of the Lie group SU3, special unitary group. So there is a close connection between this and SU3. So today we will define Weyl group using the Lie group. But later on, there is a way to define this just using the Lie algebra itself. I think that's easier for our purpose. But for today, we will use the first approach. So first of all, we have to define subspace H spanned by H1, H2. The Cartan subalgebra of SL3C. This is the definition. The Cartan subalgebra is the space spanned by H1 and H2. All right? But in fact, we have an explicit description of this. What is that? As a matrix. H1 is a matrix, diagonal matrix with entries 1, 0, minus 1. H2, 0, 1, minus 1. They are both diagonal entries, so it must be space of diagonal matrices, and the trace is always 0. So in fact, that's all. So it's a set of all diagonal matrices A, B, C, where the trace is 0. The Cartan subalgebra is like that. Do you think it's a Lie subalgebra? Is this a Lie subalgebra? Okay, let's vote. I think it's a Lie subalgebra. Raise your hand if you think. No one? Okay. Raise your hand if you think it's not a Lie subalgebra. Okay. I see. Maybe it's my fault then. No one understands? Okay. Here is one trick. It should not be a Lie algebra, Lie subalgebra, because if it was, then we would call it Cartan Lie subalgebra, right? But we didn't call it that way, so it's not going to be a Lie subalgebra, QED. Of course, that's not. But this, what happens if you apply H2 to it, or X1 to it, or H1? What happens if you apply this? It goes outside this, if you apply this. So it's not a Lie subalgebra. If you apply H1 to it, it goes outside. Because it's, what is this? Yeah, minus X1, 2. It goes outside, so it's not a Lie subalgebra. But it's a subalgebra, of course. We have like a multiplication here just by themselves. All right. And we're going to introduce two more notions. N is now we are using Lie groups. ADA H is in H, for all H. What does that mean? Oh, so this is, by the way, the action, conjugate action. We apply A inverse, left and right. So for every element in our Cartan subalgebra, if you apply this adjoint action, then it stays there. That means N this really acts on H, because it never sends something outside H. So you can say that N actually acts on H. We just collected them so that they can form a group and they can act on H. But there will be many things that act trivially, so we want to mod this out by those. So Z is a subgroup consisting of matrices in SU3 such that it acts trivially. Not only in H, but it's just exactly the same thing. Both are groups, and this is sitting inside N. It turns out that, then by definition, as I told you, N acts on H because of the condition. Okay? By, of course, by this. And Z is in fact a normal subgroup of N. This will be one of the homework problems. And Z fixes the whole space, because that's just a definition, right? So we have an N action, and we have a normal subgroup that fixes everything in this action. That means we can model out this. We can consider N mod Z. This is a group, quotient group. This, in fact, acts on H. How does this act? In this way. If W is an element in this group, then we have a representative like A plus Z. Take any representative of this quotient group element, then the action will be just A times the action coming from A. And this is well defined because of this. If you take a different representative, it will give you the same answer because Z fixes everything. So it's a well defined action. And this is the Weyl group. So this is the Weyl group. So definition. The Weyl group of SU3 is just W, N quotient Z. And this acts on the Cartan subalgebra. We will later see a definition of the Weyl group using just SL3 or just Lie algebra. And and it turns out that this can also be written as generators and relations in the usual group presentation. And this turns out to be a Coxeter group, if you know what that is. So it's an example. Weyl groups are Coxeter groups. And W for this is isomorphic to S3, which is the symmetric group of elements 1 to 3. So it has 3 factorial 6 elements. There's permutations of n over 3 elements, 1 to 3, 1, 3, 2, etc. Yeah, so Weyl group is finite. N is of course not finite, but if you mod out this by Z, it's going to be a finite, and it just has just 6 elements. So we know that this Weyl group acts on the Cartan subalgebra, H1, H2, or span of that. But we also want to know in this section, our goal of this section is prove. Yeah, actually, I'm not going to prove, but let's write this way. Prove that this Weyl group is a symmetry of weight for any finite dimensional representation of SL3. Okay? That means this acts on the set of the weight of any representation. So if, in other words, if pi is a representation, and let's say W, okay, of pi. We have a set of weights. It'll be finite. If we have a finite, then what this statement is saying is that W acts on this. W acts on this. Yeah, but to explain this in a precise definition, we need to introduce some more concepts because we don't really know yet how to apply this action. The action is not defined just yet, but we will give. I'm going to tell you that in a moment. But that's the goal. So this is very useful tool to understand representations. But before that, we have to introduce a new definition for weights. Okay, so what is the definition of a weight? A weight? To talk about a weight, we have to have a representation. So weight of something, a representation, is just a pair of numbers, which are in fact a pair of integers, such that pi h1 m v equals such that there exists non-zero vector v such that this is m1 v pi m2 v equals m2. So basically, a weight is a simultaneous eigenvectors. That's eigenvalues. That's how we understand this. But now, in this case, consider any h in our Cartan subalgebra. That means we can write this as a linear combination of h1 and h2. Okay? That's the definition. And what is pi h applied to v? Let's see what happens. With the same weight vector, this is pi h1, so a times v, b times pi h2 v. I just use this stuff. But what is that? A times m1 for this, p times m2 multiplied to v. So again, v is an eigenvector for this operation. For any element in our Cartan subalgebra, pi of h will have eigenvector v eigenvalue, something like that. h1 and h2 are just some of them. Okay. So eigenvalue for pi h. So we only, in this definition, we only specified eigenvalues for just two operators, h1 and h2. But why not H1 plus H2? Why do we have to have only this? What about A2, H1, H2? Maybe we could have defined, okay, I'm going to define M1, M2, M3, where this is weight eigenvector for H1, this is H2, this is H3, which is, let me define this way. That can be a definition, right? But why do we have 3? Well, I'm going to have M4, where this is a eigenvalue for H operator H4, which is like, I don't know, H1 minus H2. Are we satisfied now? There is something missing here. Again, like let's say M5. This is H5, which is like 2H1 plus 2019 H2, etc. No matter how many values you add here, there will be always something missing. But we want to say that mu is our goal is to express or define mu such that we contain everything, not just M1 and M2. Of course, if you know M1 and M2, we can construct everything, but we want to somehow record them all at the same time. Can you do that? We cannot do that just in this way, but there is a way to do this. What is that? So the idea is, whenever you have an element here in H, we want to get a number corresponding eigenvalue. For this, we want to assign this. For this, we want to assign this, etc. For this, we want to assign this. For any element in H, we want to assign some number, which is a complex number. This is called linear operation. What is that? Linear functional. So weight is going to be a linear functional. Whenever you have something, that will give you eigenvector, eigenvalue corresponding to this. That's basically the definition. And that will be more convenient for our purpose because, first of all, we don't have to specify what H1 and H2 are. These are just special vectors that we chose at the beginning. But usually when we do linear algebra, we want to say things, statements, without specifying vectors. We sometimes prefer basis-independent definition. So that's why we want to do this. So here's the definition. A weight of pi is now not just a pair of integers or complex numbers, it's a linear functional mu from the Cartan subalgebra to complex numbers such that there exists a non-zero vector for all h in our Cartan subalgebra, pi of h, if you apply this, mu of hv. So mu of h is like m1 or m2. This is an corresponding eigenvalue for this specific operator. Okay? Yeah, this might be a bit confusing if you look at this first time. Maybe you prefer m1, m2. That's easier to understand. But this is a very useful idea. And if you want to define this action, Weyl group action, we really need this kind of definition. Okay. So, like, before weight was just m1, m2, but now mu is just linear functional, which means for everything you get a number here. So this, in fact, they are not really different. They are really the same, but only in different definition, different expressions. So this means mu h1 is m1, mu h2 is m2. Once you specify these two numbers, it completely determines this linear functional. So really, this, even though it has only two numbers, it contains the full information. So they are really the same thing. So sometimes we will use this, but sometimes we will use this notation. But next time, we will also have another way to writing this. So there will be many things. So it's kind of one thing that might be a bit frustrating when you learn new things is that there's one object, but there are so many ways to look at it. There are so many ways to say, like, sometimes weight is this, but sometimes the weight is this. They are all, although they are all the same. So it's really important to be able to understand in different aspects. But eventually they will be the same. Okay, then I think I should stop here. Thank you for your attention.